Alright, so in this video lecture, let's learn how we can apply calculus into finding arc lengths of those curves that are represented in polar coordinates. So for short, our discussion title here is arc lengths in polar coordinates. Okay, and so arc lengths. So now at this point, it is evidently clear that we have to learn about how to calculate arc lengths here on the polar curves after you have learned and understood well what a curve in polar coordinates is and how to operate and how to graph a curve in polar coordinates. Okay, and so in case you haven't learned, then make sure to either pause or exit out of this video lecture and find my other video lecture where I gave an introduction to polar coordinates as well as how to graph polar coordinates. How to graph curves in polar coordinates, and then we're gonna advance and proceed into this particular lesson right here. And then another requirement is that this video lesson here, this video lecture here, must be viewed or learned after you have learned about how to what a definite integral is and how to use the fundamental theorem of calculus to evaluate a definite integral. Okay, but other than those required understanding, then here we go. Let's dive in. So back to what I was in the middle of saying, arc length. Now, as you have already seen through your study with polar coordinates and as well as and especially how to graph a polar curve, then a lot of times polar curve and or in general a graph is generally in a curved shape right here, and that's a polar curve. Okay, so any curve or any polar curve, more specifically, has a graph in a bent shape like this. And so now, instead of taking the full curve, or it could be a full curve, or we just simply gonna take only a portion of our complete polar curve. Okay, so let's say instead of taking the complete polar curve, we're gonna take only one portion of the polar curve. Okay, we're going to take one portion of the polar curve and we want to find out how long that piece of arc is. Okay, or so with this piece of curve right here, that's what we're doing by, that's what we're learning how to define right there. We're finding the length of those arcs, those pieces of arcs on any particular polar curve right there. Okay, and so now just the same polar curve, you can draw another polar curve right here, and we, instead of taking the whole full polar curve, which we can also do that, okay, but here more specifically, if we take only one portion of the polar curve, okay, what we have there is an arc. Okay, and so that's the idea of what we're getting into right there. So I was just giving a preview of what's going on. All right, and so now after that brief introduction of the idea right here, then let me stay back with this particular curve right here. So this is one fundamental that applies because you will be throughout the quarter that you are learning calculus here. Then there will be quite a few occasions where we are applying our understanding in calculus into finding the length of the curve. And so specifically speaking, this curve here is represented in terms of polar coordinates. Okay, but this is one fundamental. You might have seen or you might have not seen the general fundamental yet. So here it is. But anytime we're calculating arc lengths or the length of a curve or a piece of curve, a short segment of a curve, anytime you're doing that, then we think about partitioning the curve into infinitely as many subsections as possible. Okay, so any curve, doesn't matter if it's a rectangular coordinates curve, that means the curve that's represented in Cartesian coordinates, or the curve that any curve that is represented in polar coordinates. Any of those curves we can always, because a curve is a physical curve itself, so any of those curves we can always break it down or divide that into the subsections like this, sub-intervals like this, or I mean subsegments of those curves again. Okay, so each of these subsegments right here, let's call them, it's a small change in curve length, so let's call that it's a ds. Okay, so each of those, that's a ds, that's a ds, and that's a ds. So the idea now is that the more we break it down, okay, the more we break it down, then the better approximate that is. So, and so now each of those subsections, the idea now is that each of those subsections, if we think of that, then when it's small, then being bent or being nearly straight is almost the same. So I'm trying to draw in my picture right here, okay, the actual ds when it's small enough, right, and being a bent can be close enough to being straight like that. Okay, and so in that way we will take advantage of that later. We will take advantage of that nature a little later. But now, I did not tell the complete truth just earlier about the ds here, but the idea is, if as long as the ds is still a recognizable amount like this, then that's not the true ds. The idea now is that we're gonna keep breaking it down into more subsections, more sub-segments along the curves here, along this particular curve. And so in the end, and at the end, when we have infinitely many subsegments right there, then each one of these becomes infinitesimally small. And so now to achieve the actual length, of this curve, of this total curve, then we're going to say length of the curve is going to be, as a fundamental, the accumulation. And this is where we apply our calculus understanding. So the length on any curve, the length of any curve, bent curve, straight curve, the length of any curve is accumulation of all of those little segments like that. That's why I call that the ds. Okay, it's accumulation of all the little segments, and we're accumulating from a start to an end. Okay, we're accumulating from a start to an end. Okay, and so now things are starting to get a little. It could be a little dangerous in a way that we identify start and end. So the same curve, it also depends on the direction where the curve is going. So some curve is pointing this way right here. So start could be that point and end could be this point. Or some curve is starting here, this point, and ending at that other point. And so start could be here and end could be the other one. So in every problem, there will be a way for us to identify where the start and where the end is. But now, generally speaking, as a fundamental, then anytime we're calculating the length of any curve, of the length of any piece of curve, then we're going to think of that as a partition of infinitely many small sub-segments right here. And then we're going to accumulating the length of all of those sub-segments from a start to an end. And that's how we achieve the length of our curve in total. So that's the general fundamental. Either you are working with curve lengths, with arc lengths in polar coordinates for those curves that are represented in polar coordinates, or for any of those curves that are represented in rectangular coordinates or Cartesian coordinates, or even curves that are represented in parametrically. Okay, so that's the fundamental. So now, what's special about the polar curve? What's special about those curves? So now we're going to take this fundamental and apply that into the kind of curves where the curve itself is expressed in polar coordinates. So this is only a fundamental. Okay, and so now before I get any further, I have to remind anyone that the idea that when you are graphing any polar curve, then any point on this curve is represented by a radius, how far that point is made, how far that point makes from the center, and that's the radius. And then from where that point is on the curve right here, how much rotation in a positive direction. Okay, so the rotation here is the angle theta, how much angle theta representing the positive rotation, and usually from the positive x-axis. Okay, so how much angle that is opening up from in the positive rotation. Okay, and so any point there is r comma theta. Okay, so that's any point. That's the way how we represent any point on a polar curve in terms of radius and the angle theta. All right, so in that way, so now back in the general discussion about the polar coordinates, and then in some other applications, I have brought in the idea that so now anytime that we're thinking about a polar curve, then we always think of a positive rotation. So in the way how I'm drawing this specific curve right here, then this has to be a start. Okay, this has to be a start because at this point right here, we have some small angle, theta 1. Okay, and then when we end that curve right here, the rotation once again goes in positive direction. That is that is counterclockwise in common daily term like that. And so when we arrive at that point, the rotation has to be at somewhere, at some larger, okay, at some larger theta that we call it. It's a theta 2. So this is theta 2. Okay, and so the start here. So now in this polar curve, the curve here is the kind of curve that's created by the change from theta 1 to ending at theta 2. So later on, we're going to incorporate that into our start and end of the polar curve. I mean, of this this general fundamental to find the curve length. Okay, but now let's even dive in a little further. I'm going to use my other board to derive a couple understanding. So now let's look at the ds a little closer. So I brought this up earlier. The ds is really meant to be a very small subsection. Okay, so this is a ds. It could be curved, okay, or it could be straight. It could be curved or it could be straight. But the idea now is that pretend that this small subsection here is an infinitesimally small subsegment of that curve that we're looking at. So at a very small or microscopic level like that, then think about there is not much difference between being bent or being straight. So either the curve, either the subsection there or the subsegment there is being bent or being as an arc or being straight as a segment right here as a straight segment. The length is close enough from each other. Okay, so in that way, like I said, so my point now is that when it's so small, then even being bent or being straight, it's just almost indistinguishable. Okay, almost indistinguishable to the point that we can kind of interchangeably use them. So now in that way, just pretend that if that bent length right here is about the length of that straight segment at the microscopic level, indistinguishable, that's the term I was using, then in that case, in a different picture. Now let's really get straight to the point. If it was straight, if it's straight, because a lot of time, like I said, in a very microscopic level, then being bent is not much different with straight. So if this is the ds, then in a triangular setting, then we can have a right triangle like that. So this small distance now is going to be our dy, the infinitesimally small change in the vertical coordinates. And then this in this right triangle, then ds is the hypotenuse. So this length right here is one of the two legs right here, and that is the infinitesimally small change in the x value or the horizontal coordinates. Okay, so right now I'm sticking with the rectangular coordinates, and you will get my point later on. Okay, but so apparently, right from Euclidean geometry, immediately from Euclidean geometry, then we know that hypotenuse square equals the sum of the two squares on the two legs here. So that means mathematically ds square equals dx square plus dy square, and I should have put these in parentheses. Okay, that comes straight out from Euclidean geometry. Okay, about so this is ds square Pythagorean theorem. Okay, ds square equals the hypotenuse square equals the sum of the squares of the two legs right there. Okay, these are the two legs, the two straight edges. Okay, the two vertical edges, the two perpendicular edges on that right triangle. Okay, and so that further means ds itself can be done as the square root. Okay, and everything I'm doing here is again, as a reminder, everything I'm doing here is at the level where the ds segment here is infinitesimally small, so that there's no difference between whether it's bent or it's straight. That's the main idea right there. One of the big arguments like that, right there. And so now at that microscopic level, each ds will be equals to the square root of dx all square plus dy all square. Okay, and that's what I'm doing for now. So everything, anyone viewing the video and following along with me at this point is starting to wonder, why am I all of a sudden direct your attention into the rectangular coordinates. Even though we started our lessons, and I was saying clearly that we want to find lengths of curves that are in polar coordinates. Okay, and it looks nothing polar here yet. Okay, it will come. So now, at this point, think about this. We can always algebraically do the following. In this square root expression, I can always do the following expression. I'm going to factor out a d theta from this expression here, which at the moment has completely no theta. But algebraically, I can always factor out a d theta square as a matter of fact. Okay, so factoring out a d theta square factor from each one of these two terms here will leave for me inside a pair of parentheses is I'm looking at a dx over d theta square plus a dy over d theta square. Okay, that's what happened when I factor out an infinitesimally small change in theta, and theta is sort of like a third party expression that at the moment here it was nowhere in the formula, but then all of a sudden we can algebraically factor it out. Okay, but now at this point, after we factor out a d theta square right there, then a little more further step, I can bring that d theta square expression outside of the square root, and then as we bring that outside of the square root, it's gonna become just d theta itself. So another a rewritten form of this square root expression is that we having square root of just the dx d theta all square plus, okay, and then we're looking at the dy over d theta all square, but then we multiply with a d theta in front. All right, so things are at least up to this point getting closer to seeing things in polar, because now I'm starting to show the d theta expression, and theta is the angle change. Theta is the change in angle. Theta is the change in angle for any, or theta is the variable that determines where our point on the polar curve is at. Right there. So there's theta is one of our variable, and we're starting to see d theta in our expression here. Okay, so things starting to get back to polar coordinates. Okay, so now, but let's look a little further into each one of these expressions, each one of these squares inside of the square root right here. Here I'm looking at dx d theta all square, and here I'm looking at dy d theta all square. Let's give that a moment to think about. Let's give it a moment to think about the dx d theta here. Now recall from our general understanding about polar coordinates. This is from it doesn't have to be right in your calculus course. It could be that you learned about some general understanding of polar coordinates even prior to calculus. Okay, and here, even though we're doing specifically calculus course, but a lot of your work here will link to previous course. So right now, this dx and d theta right here recalls for us that from fundamental understanding of polar coordinates, then we always express x as r times cosine theta. X is r times cosine theta. This is the formula where we can go from, see, r is the radius and theta is the angle of any point. So multiplying the radius and cosine of theta will give us the x coordinates in rectangular coordinates for any specific point on a polar curve. And then similarly, the y coordinates, the y rectangular coordinates of any points on a polar curve can be expressed as r times sine theta. So these are the two important relationships that relates between that converts between a point in polar coordinates to a point in rectangular coordinates. Like that. So, but now mathematically speaking, I see that x is an expression that r is an expression r times cosine theta, and y is an expression r times sine theta. Okay, so this is some fundamental relationships. But then from that further, from that understanding, we further learned that back in our days learning about just the general understanding of polar coordinates, it could be a course before your calculus course here, or just be some days that you've learned within this course of calculus, but you've learned some introduction to polar coordinates. So according to the introduction of polar coordinates, now when we draw a polar curve, then r itself is usually some function of theta. This is the way how we represent a polar curve. Any polar curve is represented, at least for beginners, right? More commonly, a polar curve is represented, as I have explained quite a few times, a polar curve is more commonly represented as a function r of dependent on the variable theta. Okay, so r as a function in terms of theta, that's for short. Okay, and so I can take that. So according to this relationship, r equals a function of theta, then we can take this relationship and substitute it back to each one of our x and y coordinates right here. And so consequently, I have to erase such an important information there. So now consequently, x here, since r is a function of theta, x can be re-expressed as f of theta, a function of theta, times cosine theta, because this is radius and this is cosine of theta. That's one of them. And so now in that way you will start seeing where I'm going. So now all of a sudden I'm realizing that x can be entirely expressed as a function of theta. Okay, x is a function of theta. Okay, and then in another argument I can make here before we get back to that to some more explanations about that square root expression. But so in that way, since we already knew that r is a function of theta, then consequently y as a coordinate, as a vertical coordinate, can also be expressed as f theta times sine of theta. Okay, because this f of theta is r, it's our radius. This is radius and this is sine of theta. So we're just substituting f of theta into the place of r in those two relationships between polar coordinates to rectangular coordinates, polar coordinates to vertical rectangular coordinates. Okay, and so now again I recognize, similar to how I recognize the x coordinates, so y coordinates can also be expressed as a function of theta. So here we have x of theta and y of theta, and these are two functions completely in terms of theta. Okay, there are two different functions, two different separate functions, and they're both dependent on theta. Okay, so now how is this related to what we're seeing here? So now this is what I'm seeing. Wait a minute, so dx d theta has to be in this way right here. Dx d theta has to be the derivative, of this function x in terms of theta, because in this way now how we have expressed and how I have made a whole bunch of arguments, then this function x right here is clearly a function of theta. So we can apparently take the derivative of that function x in terms of theta. Okay, and then we can take that and then similarly dy d theta. Now I can recognize that as the derivative of this function y. Y is a function. We recognize this derivative in terms of theta. Okay, so dx d theta, dy d theta is the same as y prime of theta like that. Okay, and so now in that way we keep that here as a goal right here. Let's I'm going to erase the board here. Okay, and let's think even a little further. Okay, it's such a beautiful world of math out there where things are linked together and connected. So let's start out with this. Now with this understanding that now we understand x can be expressed as a function of theta, primarily some f of theta, that's radius times cosine of theta. Okay, so generally in this way right here, generally what can dx d theta be as an expression, as a general expression? So anyone at this point in your calculus learning is fluent enough with this. There we have a product, and so x prime of theta, this is a shorter symbol for dx d theta. Okay, so this has to be according to the product rule. Then we're going to look at f prime of theta, okay, times cosine of theta plus, now I'm going to keep f the same, but I'm going to multiply with the derivative of cosine theta, which gives me a minus sine theta. Or in other words, x prime of theta, the derivative of x in terms of theta is f prime of theta times cosine of theta, and I'm going to subtract, okay, I'm going to subtract f of theta times sine of theta. That's one fundamental important, another relationship that we derived, okay, that we derived so that we can eventually serve this purpose right there, okay, so that we can serve that purpose. So later on I'm going to bring this and substitute that expression in here, and then the square is going to take that into a whole next level of fascinations. Okay, so similarly, so this square root expression, the other square term involves a dy d theta. So dy d theta. So y, okay, so now I'm going to have to erase this. Let me write that in a shorter notation right here. So x prime of theta equals f prime of theta times cosine theta minus f of theta times sine theta. Okay. Times sine theta. Okay. And now let's look at another result right here. So we have also understood that y now in our understanding can be expressed as a function in terms of theta. So, and that is y of theta equals some function of theta, this is radius, okay, times sine of theta. Okay, so this is completely together, it's completely a function of theta. But now recognizing this as a product right here, then I'm going to find y prime of theta. That is going to be according to the product rule, because there's a product here. Okay, we're looking at f prime of theta times sine of theta without derivative, plus, now I'm going to leave f of theta here without the derivative, and I'm going to multiply with the derivative of sine of theta. And in your understanding of calculus, up to this point, derivative of sine theta is going to be cosine theta. Okay, and so this is another important formula for, and this is an expression which eventually can be substituting for that dy d theta expression right there, or substitute into that dy d theta square expression right there. So we have these two fundamental results. All right, so now let's apply. Allow me to erase these steps right here, and I'm only going to retain this current expression. So all right, so now currently ds is a square root expression, which involves dx d theta all square plus dy d theta square, and we're multiplying that with d theta. Okay, and so now that means in this square root expression, dx d theta is still here on my board. Okay, and so I'm going to substitute that in, and what I'm having now is a very lengthy expression. I'm having a little bit of a hard time organizing the space right here, so how about allow me to, okay, so just think about it this way. Now before I get any further into the square root, let's just think about the x prime of theta all square. Okay, that is the square of, we are going to square this expression right here. We are going to initially square this expression. And that's, now we're going to FOIL out that expression here that gives me f prime of theta. Okay, square times cosine squared of theta. Okay, and minus 2 f prime theta f theta cosine theta and sine theta. Okay, that's after we foiling, and then I'm going to add with f of theta square times sine square theta. Okay, and so that's the square after we FOIL out this square right here of two terms. That's how it gets right there. In the meanwhile, y prime of theta all square has to be So it's going to be the square of this expression right here, f prime of theta in sine theta, okay, plus f of theta cosine theta all squared, and that gives me f prime of theta all squared times sine squared theta, okay, plus, and then 2 f prime theta f theta sine of theta and cosine of theta. Right, and I want to add f of theta all squared times cosine of theta. All right, so that's how I squared out and FOIL out this perfect square right here. So now, in this expression, dx d theta squared plus dy d theta squared means I'm going to add this expression and that other expression. So I highly recommend you can also start taking your time doing this together with me right there. We're just simply going to add that expression with this expression. Okay, so now I'm going to need my other board. So in that way, how I see that now is that, so dx d theta all square plus dy d theta all square. Let's just specifically handle this expression right here. So what I have now is going to be, so for the dx d theta square, I am going to first substitute this lengthy expression here, this whole lengthy expression. Okay, this lengthy expression, I'm going to substitute that into my dx d theta all square. So that gives me f prime of theta, okay, all square times cosine square theta, okay, and I'm subtracting 2 times f prime theta times f of theta times sine theta times cosine theta, okay, and plus that f of theta all square times sine square theta. And now I'm going to add, so now it's a big add right here. Now I'm going to add with that whatever the expression for dy d theta all square. So let's look back at the other board to find out what that dy d theta all square is. So dy d theta all square is finalized at this expression right here. Okay, so go ahead and take notes, and I'm going to copy this down, and I'm going to substitute this expression into the place of the other board right there. So now I'm looking at, so adding with the dy d theta all square, that gives me f prime of theta square times sine square theta, okay, plus, and then 2 times f of theta. I already ran out of space right here, so I'm going to jump down to the next line, plus 2 times f prime of theta times f of theta sine of theta cosine theta, okay, and add f of theta all square times cosine squared of theta. Okay, but at least that's the end of our sum right here, of our expression. So now let's start looking for some cancellations that can happen. So I see that the 2 f prime theta, f theta, sine theta, cosine theta is opposite with that term right here. So all that here is gone. Okay, and now the sine square term, okay. And actually, let's not look for sine square term. Let's look for something like this. Let's look for the f prime theta square term, f prime of theta square term. Let's group these two. And so what it gives me, so right now we're still working out with that dx d theta square plus dy d theta square. But what remains for us? Now allow me to write this as following. These two terms, I see them as like terms. Okay, those two terms, I see them as like terms. So I'm going to factor out that f prime of theta squared. So f prime of theta all squared being factored out. And what I have left behind in parentheses is a cosine square of theta plus sine square of theta. That's down with 1. Okay, that's down with one term, one pair of expressions, and then start thinking ahead of what this will consequently become. The next one here I'm looking at is going to be these two, or now allow me to underline them with squiggling line to indicate that they are like terms. Like terms in the sense that they both contain that f of theta squared, not f prime, f of theta squared. So f of theta squared can be factored out. Okay, and now I have in parentheses is sine square of theta plus cosine square of theta. Okay, and so now this is 1. That sum is famously known in trigonometry, equals 1. That sum is famously known to equal 1 as well. So in the end, we break down to f prime of theta all square times 1 plus f of theta all square times 1, because that is 1. All right, but now I brought this up earlier. What do we recognize about this? This is r. This is the radius expressed as a function of theta. And so, and this is now dr d theta. That's how I see it. So now really this dr d theta, the derivative of radius as a function of theta. Okay, dr d theta square plus r square. Okay, so it came down to a shockingly reduced expression right here. So now, after all that, I need to get back on my other board, clear out some details right here, and then I'm going to go back and fill in this work. So all that scratch work earlier is now getting us ready for this. And so just now on the other board I have explained dx d theta all square plus dy d theta all square is equal to, so now it's square root, and then these two terms added together is equal to r square plus dr d theta all square. Okay, so that means our ds is the square root of that sum of two squares times d theta. All right, so now once we have found that, and think of our integral, the length of any curve in polar coordinates is from some start to some end, okay, it's accumulation of infinitely many subsegments, okay, from start to end. But each of the subsegments here is represented by this lengthy expression with the square root, but at least it's not that lengthy anymore. So now it's the same as an integral on some interval of changing of angles from some start to an end. Okay, and then here we are multiplying with the square root of r square plus dr d theta square, and then d theta. So this work right here now, before we worry about the start and the end right here, this work right here is specifically good on any of those polar curves which we pay most of our attention to. This formula is good for any of those curves that are expressed as a function r, as a function in terms of theta. Okay, so any of our polar curves that express r, the radius, as a function of theta, then we have this formula that will work directly into finding arc length, the length of any curve in polar coordinates. Okay, and so in that way, now let's search for the start and to an end right here. So in my explanation of the picture I've had earlier, now sadly I erased that on the other board. So let's make that quick picture here. So again, any polar curve, right? So now any polar curve, the agreement I have set any one of my students into is that when we're looking at polar curve, then we're always going to view the rotation in positive direction. So in positive direction, then some smaller angle theta 1 is here. Okay, positive direction is counterclockwise rotation, and then a larger angle theta 2 is here, where it reach that other terminal end right here. Okay, so that means that we can use theta 1, some theta 1 to some theta 2 as being the start and being the end of our accumulation. So we're accumulating all of those segments from angle starting at theta 1, okay, and ending at theta 2 right here, and that's finished our formula. So now officially we're having a formula for arc lengths. Arc lengths, in calculating any arc length in polar coordinates, we can go as an integral from theta 1 to theta 2. It's an interval of angle change here. And we multiply with the square root expression r squared plus dr d theta r squared. Okay, and we multiply that with d theta. This is, ladies and gentlemen, once we have expressed any of our polar curve as a function r in terms of theta, a function r, so r is a function, but in terms of the variable theta, then we can always use this formula as the formula to calculate the length of any polar curve, or at least any piece of length, okay, the length of any piece of the curve, okay, from an angle change from theta equals from theta 1 to theta 2. All right, and so now that's the fundamental, and that's the formula that we are going to be using. So now we are ready for heading into some example. All right, so let's now look at our first example, example 1. And let's look at the wording of the problem right here. Quite straightforward. Let's look at find the length, okay, of the curve r equals 1 plus cosine theta. Okay, but then we want only the length of that piece of curve on the interval from minus pi over 4 to pi over 4. Okay, so we want to find the length of the curve, this polar curve right here, on that, over that interval from minus pi over 4 to pi over 4. So it's not the full curve, okay, it's just the curve that's restricted in this in between this interval of angle change right here. So let's have a picture of that. Let's have a picture. So I won't have enough space to draw the actual picture here, so allow me to swing over to decimals like that to show the picture. All right, and so now on my graphing calculator, on my graphing device here with decimals here, let's look at so this is the graph, okay? This is the graph for 1 plus, this is the polar curve, okay? For 1 plus cosine theta, okay? 1 plus cosine theta. And so, but then this curve is already a full curve because that's a full rotation. And let me demonstrate the whole idea about a full rotation right here. Okay, so here's my handle, okay? And so when theta is equal to 0, in a positive direction, when theta is at equal to 0 right here, then this point right here is indicating from the pole out to this, we have some radius, okay? And then as we are rotating the angle in a positive direction, you see how we notice how we start getting see as the angle here rotates, right? We start having the different radiuses right here, the different radii right there, and so the radius keep changing its value, right? And now I'm about to complete my 180 degrees turn right here. So it's a rotation of pi right here, and we've had about half of that complete loop right here. Okay. And then I realized I didn't zoom it in close enough. And then now I'm gonna move my angle. So see, you can see that the angle now is opening past 180 degrees. And so as we are completing, this is at where we're at 3 pi over 2. And now when we complete the whole rotation, the entire rotation at 2 pi, right here, okay, then that's where we have a circle. I mean, that's where we have that complete loop, looking just like the loop we have had earlier here. Okay, but now, unfortunately, the problem did not ask us to calculate the length of the complete loop here. Okay, instead, the problem only asked us. So let me roll back to the 0 out. The problem was only asking us to calculate. All right, so you see how I put my starting angle here. The problem wants us to calculate the piece of the curve where it happened only from angle change minus pi over 4. So minus pi over 4 is here, and ending at pi over 4. So let's look at the change right here. Let's see how the curve is made. So as I'm going from negative pi over 4, that's my start right here. And then I'm ending at, okay, and I'm ending right there at a positive pi over 4. So this is positive pi over 4. So we're starting at negative pi over 4 down here, and we're ending at positive pi over 4. What's the length of that curve? That's what this question is asking. That's what this question is asking. Okay? And so now we're seeing, so instead of getting the complete full curve, the length of the whole full curve right here, we're only getting the length of that piece of curve that happens from minus pi over 4 to pi over 4. So the rotation is still going positive, but it's just not the rotation that starts at 0. It's just the rotation that starts at negative pi over 4 down here, and we're moving in the positive direction. All right. And so now, after seeing the picture over here, let's start getting into the problem. So gladly, and just as I said, we are, for us here learning most of the time, or more primarily, we're going to focus on those kind of polar curves where it expressed r as a function in terms of theta. So this is everything we have right there. So r is a function of theta, and then we have an interval. So this is our start, this is our ending of the accumulation. And so now we have everything ready. So if we're looking back at the formula one more time right here, the formula was stating that we mainly need to set up a square root expression. We have r squared inside the square root and dr d theta. So now in our actual problem here, let's spend some time deriving dr d theta. Okay, and we're going to put the pieces together. So from this expression dr d theta, okay, from this definition of r right here, dr d theta has to be minus sine of theta. No doubt about it. Okay, anyone learning calculus up to this point should be fluent with this. And then taking the derivative is just as usual. Okay, and so now that means dr d theta r squared, and I could have saved this step for later, but since I wrote it, then we can just get started on that. So it's like that. Okay, or we can alternatively write it as, or we can further write that as a sine squared of theta. Okay, and so now we are ready for that setting up right here. The length that we're looking for, the length of this curve is the accumulation. Okay, all of those little segments right here is done as, so this is 1 plus cosine theta r squared. This is r squared, okay, because r equals 1 plus cosine theta. So we purposely we substitute the entire expression 1 plus cosine theta into our r squared. And now I'm going to add with dr d theta r squared. But dr d theta r squared is sine squared of theta. So that gives me, and include that in the parentheses, we're looking at sine squared of theta. And then we have a d theta expression out here. Okay, so we're almost complete with our integral setup. Let's do a couple checkpoints right here. Again, our expression here is a d theta. So now I'm going to check for consistency before we move on. We question ourselves, are all these terms in terms of thetas? Yes, they are. The entire square root expression here is in terms of theta. So now we're good to go. It's consistent. The main variable here of this expression is consistent with our d expression here. Okay, and so now we are going to be accumulating from the angle that's changing from minus pi over 4 to pi over 4. All right, so all that here is a ds, okay, the length of one sub-segment, and I'm talking about an infinitesimally small sub-segment. That's why we call it, it's a ds. Okay, and so now once we've gotten up to that point, and now we have completed our integral, and now it's just time to calculate. Now it's just time to calculate the actual the value right here using the fundamental theorem of calculus. But now notice, and let's look back at the picture one more time, and we're going to try to find way to improve our integral before we actually use the fundamental theorem of calculus here. So looking back at the picture, you can see that this piece of the curve, or for the full curve, it's actually quite a symmetric curve here. The curve itself, the polar curve itself, is quite symmetric. And so this is from 0 to pi over 4. That piece of the curve right here from 0 to pi over 4 looks like it's exactly half of the whole full curve. I mean the whole complete length that we're calculating is from negative pi over 4 to pi over 4. But since we're taking advantage of the symmetric nature or the symmetry of our curve right here, then we can go from 0, from angle change from 0 to pi over 4, and then we're going to double that length right here. That gets us the complete length of our designated problem. Okay, that gets us the total length of our overall problem right here, which goes from minus pi over 4 to pi over 4. So in that way, and as I said, we double half of each of this length that we're calculating, because now we only want to make life easier for us a little bit by going from 0 to pi over 4, and then we double that. And so now before I rush into using the fundamental theorem of calculus, I am going to rewrite this as or I'm going to write it in my next line below right here. Okay, it's a 2 times, and it's an integral from 0 to pi over 4. Okay, and then now the square root here. Now in the meanwhile, we can start foiling out this square term right here. So it's a 1 plus 2 cosine theta plus cosine squared of theta. Okay, and plus sine squared of theta. All right, in the square root and then times d theta. And then we recognize further that cosine square of theta plus sine square of theta is a 1, and then 1 plus 1 is a 2. So allow me, instead of writing as another step, allow me to just erase out some terms right there that's modified, okay, and combine. And so that's what I just erased there is a 1, but 1 plus 1 is a 2. So our overall expression here is the square root of 2 plus 2 cosine theta d theta. All right, you can write this as the next step, or you can just do that right here, depending on how mature you are in mathematics. So now we're ending up with a much shorter and much simplified expression, ready for taking the definite integral. All right, and so now in this work right here, now, so keep in mind again that we're going from 0 to pi over 4, but then we are going to double that. All right, so now I am going to, in this way right here, I am going to also, now think about inside the root here, we have a common factor of 2. Okay, so we can, so scratch work, we can factor out, it becomes a 1 plus cosine of theta. Okay, but in the square root, so bringing that outside of the square root, we're looking at the square root of 2 times square root of 1 plus cosine. So this is what I mean, it's a square root of 2 times the square root of 1 plus cosine theta. And this expression is even shorter, at least in the square root here, and I can bring that the square root 2 in front. And so now in the next step, I'm doing one more step with the simplification. I'm turning that expression as a 2 square root of 2 as a coefficient, and then I multiply with the integral from 0 to pi over 4, and now it's a much simpler expression, 1 plus cosine theta d theta. All right, I am now going to move on to the other space, the other board space, clear out the board, and then let's get to work further on this integral. All right, and so now, currently we are at 2 square root of 2 as an integral from 0 to pi over 4, and square root of 1 plus cosine of theta d theta. But this time I'm purposely writing the square root expression a little large so that I can do the following. So now inside the square root, I can do the following. Inside the square root, I'm gonna, okay, and allow me to write the theta d theta all the way out here. So inside the square root, this is what I'm gonna do. I'm gonna multiply the 1 plus cosine theta with 1 minus cosine theta. Okay, and I should have done that in red ink. This is a very famous algebra trick right here. So in red ink, I multiply the conjugate of that. So 1 minus cosine theta. And I'm dividing that exact expression away. 1 minus cosine theta is divided away, and everything is done inside of the square root. Okay, and so now in that way, so without these two red ones, and the square root expression came from the previous step, and everything is there. But now in this step right here, I purposely multiply 1 minus cosine theta to that expression and then divide that away. But now there's a usefulness of doing that. Now in my next step right here, 2 square root of 2 as a coefficient, the integral goes from 0 to pi over 4. Okay, now this expression here is going to give me, now inside the square root, I'm looking at 1 minus cosine square of theta, and divided by 1 minus cosine of theta, with a d theta in front. Okay, and now I recognize 1 minus cosine square as a sine square. And so in my next step, 2 square root of 2 from 0 to pi over 4. Okay, and I'm looking at the square root of sine squared of theta over 1 minus cosine theta. Okay, and then we're dividing that by theta. I mean, we're multiplying with the d theta expression. All right, and we keep getting better and better in our integral expression, but we have not done any actual antiderivative work yet. Okay, and so now in that way, in my next step right here, 2 square root of 2, integral multiply with integral from 0 to pi over 4, and now now we're gonna start taking that sine square out of the square root. But now be careful, it's an expression, it's a square of the expression sine of theta, and when we take that out of square root, it should be solidly, it should be sine of theta in absolute value. Anytime we take square root of a squared expression, then we're going to end up with absolute value of that expression. And then depending on the domain, then we're going to decide to appropriately, right? We're going to decide appropriately to how we can remove the absolute value signs right here. So now immediately right out from the square root, it's absolute value of sine theta. But then in the denominator, we're still looking at 1 minus cosine theta, d theta. Okay, so now let's look at that sine theta in absolute value. Now the interval where we take our integration work right here, it's from 0 to pi over 4. And so at least what we know is that inside of that interval, from 0 to pi over 4, sine theta will be, okay, we know that sine theta will be greater than or equal to 0 for theta being in that angle interval from 0 to angle change interval from 0 to pi over 4. So anytime we're looking at theta being in this interval from 0 to pi over 4, then sine of theta must be greater than or equal to 0. And so now the reason I'm making this argument is that in the next step we can write this as 2 square root of 2, okay, integral from 0 to pi over 4, but we multiply that with just now sine of theta without the absolute value, divided by square root 1 minus cosine theta d theta. All right, and so now at this point we are ready for doing some substitution. Okay, and so substitution is a technique that's quite fundamental. So anyone arrive at this video lesson, usually if it's my class right here, then I deliver this lesson as an application, and after anyone has learned about the substitution methods. So now I'm going to use the substitution methods for this problem right here. So now I'm going to need more space, so I'm going to erase all that work up here and write down this current expression in this step right here. So in our current step, 2 square root of 2 times the integral from 0 to pi over 4. Okay, and then we're looking at sine theta times divided by square root of 1 minus cosine theta d theta. Okay, and so now I'm going to use the substitution method. I'm going to quickly substitute away. So if you're still feeling a little shaky, make sure you find my lessons back in earlier lessons about how we can do the substitution method. But here I'm going to choose u to equal 1 minus cosine theta. Okay, and so doing so, I am going to consequently end up with du d theta equals minus, and indeed it equals positive sine of theta due to the derivative work right there. And allow me not to remind too much about that. And that means I am going to rewrite this as du over sine of theta to equal d theta, as we recognize each of our du or d theta here is a differential, where the whole expression here is indeed understood as a fraction, as a ratio of two differentials du d theta. And so now that's how I rearranged the equation here to become du over sine theta equals d theta. And then when when theta equals 0, we're looking at u1 equals 1 minus cosine of 0. Okay, and that gives me 0. So u1 equals 0. And then u2 equals 1 minus cosine of pi over 4. Because when theta equals pi over 4, we're looking at a different value for u right here. So it's 1 minus square root of 2 over 2. All right, 1 minus square root of 2 over 2. So now I'm going to take all that here and start getting into my work. So putting all the substitution into all the substitution work into the actual problem. So now u substitute for 1 minus cosine theta. So in this expression, I am going to substitute that away. So I'm going to have square root of u, simply just that. Sine theta did not get a substitution. It's okay. Let's leave it the way it is, according to how I was teaching about the substitution method. d theta indeed does have a substitution. So we can substitute d theta by du over sine theta. So we have du over sine theta. Okay, and the two integral limits right here can also be substituted by 0 to this upper limit here is indeed I just noticed I wrote a little too narrow, so that didn't leave me enough space right here. All right, so here this is supposedly 2 minus square root 2 over 2. Okay, instead of writing that as a 1 minus square root 2 over 2, I'm just making a common denominator and write that all as a 2 minus square root 2 all over 2. Okay, and so now the sine of theta is cancelled. So in the next step, the integral becomes something much simpler. 2 square root 2 times an integral from 0 to 2 minus square root 2 over 2. Okay, and then this is a 1 over square root of u du. A very simple square root. This expression here is probably what makes it a little lengthy looking, but actually it's just one value. So the main function is here, 1 over square root of u. And so we can think of that as, so here's the coefficient, and then from 0 to 2 minus square root 2 over 2. But this 1 over square root of u, we can think of that as a u to the negative 1/2 power. Okay, and so now in that way, clearly we're looking at 2 times square root of 2. Now I'm using the fundamental theorem of calculus. So 2 times square root of 2, I'm going to multiply, and now we're looking at 2 times u to the positive 1/2 power. That's how I take my antiderivative. Okay, and now with this antiderivative, I'm ready to substitute in 0 and 2 minus square root 2 over 2. Okay, and a little further, that you can see that 2 times with that 2 square root 2 gives us actually a total of 4 times square root 2 times u to the positive 1/2. And this positive 1/2 really, let's just write it as a square root of u right here. And then we're taking the integral. We're going to substitute from, we're going to evaluate this antiderivative from 0 to 2 minus square root 2 over 2. All right. And so now the final, let's write down the next setup right here. So 4 square root 2 times square root of 2 minus square root 2 over 2 minus 4 times square root 2, but all is 0 out, because once we substitute 0 into that expression, it's all a 0 out. So we don't even need to write that term at all. Okay, and so now we are quite close to the final answer. So here what I'm looking at now is going to be, now I'm going to multiply that square root of 2, not the 4, not the whole thing with the 4, just the square root 2 inside the square root. So that leaves me 4 times square root of 2, but times 2 minus square root 2 over 2. So this 2 and that other 2 will cancel inside the square root. So my final answer now will end up being 4 times square root of 2 minus square root of 2. And I prefer to leave my answer in exact expression. So this is the answer for the arc length. For the piece of arc length, the length of the piece of arc that happens in the angle change from minus pi over 4 to pi over 4. Okay, so that's how long this arc is. 4 times square root of 2 minus square root 2. All right. All right, and let's now head out to example 2 right here. So, for example 2, it's quite a similar kind of problem right here. We want to find the length of the curve. Find the length of the curve. R equals 1 plus sine theta. Okay, R equals 1 plus sine theta. But so this example here deserves its own attention aside from example 1, in a sense that now, unlike example 1, we had a given interval. Here we only, the question is asking us in a more abstract way, find the length of the curve, period. No given interval for angle change right here. So that means when you encounter a problem like this, that means we have to find the complete length of this curve once it completes. Okay, so all right, so on my graphing calculator with decimals right here, let's look at the curve for 1 plus sine theta. Okay, the complete curve looks as following. So this is the complete curve. But now let's look at the interval change that caused completion of this whole curve right here. Let's see how what interval will complete the whole curve, because the interval was not given to us, so we have to detect that interval ourselves. So I'm going to switch over to I'm going to use decimals to detect the interval that completes our curve right here. So by default, let's just rotate from 0 to 2 pi. That's a one complete rotation. Let's default it by an angle change from 0 to 2 pi, and let's see if that gets us the curve. So right now my handle of the rotation angle is right here. So now I'm going to rotate. Okay, so as my, all right, so now I'm going to rotate, and then as my angle produce the rotation right here, as the rotation produce more angles, right? I'm about pi over 2 rotation, and now I'm up to that pi rotation, and then I will now complete to the 3 pi over 2 rotation. Okay, and now I'm going to complete to a 360 degrees of rotation, or a 2 pi rotation. Okay, and then if we go beyond one rotation, it's just going to loop over the same curve right there. Okay, so in that way, one rotation is enough. One rotation is enough to complete our curve. Okay, to complete this curve of the function r equals 1 plus sine theta. So now that means we have a clear interval. It's from 0 to 2 pi. Okay, it works just good, even though the interval once again was not given initially. So here's how I'm doing it. So now here's my setup right here. Okay, we're going to need length equals the integral, and we need from 0 to 2 pi, because we know that from start to the end, all we need is we start the rotation at angle theta 1 equals 0 and angle theta 2 equals 2 pi. And I did that demonstration with the graphical illustration earlier. And now we need a square root of r square plus dr d theta all square times d theta. So this is the general formula that we're using. All right, so dr d theta in this quick problem right here, let's do a quick little scratch work right here. All right, so dr d theta is going to be just simply cosine theta. Right, dr d theta, right from this definition of r, then dr d theta is cosine theta. So that means our expression here becomes, so as a complete integral, it's from 0 to 2 pi, okay, and then we're looking at r squared is going to be 1 plus sine of theta r squared, but now dr d theta is a cosine theta, so dr d theta r squared gives me cosine squared of theta with a d theta. And that is how we have completed, our integral setup for that. And this integral now is ready for action. But again, I'm going to take a few more steps right here to algebraically simplify down this integral before we can proceed into applying the fundamental theorem of calculus to get that solved right there. So this 1 plus sine theta all square, I can write that as a, so it's an integral from 0 to 2 pi, okay, and then that's a 1 plus 2 sine theta plus sine squared theta. That's how I foiled out that 1 plus sine theta all square. And then I'm going to add another cosine square of theta into that. All right. And now we're going to multiply with d theta. Okay. And so again, sine squared of theta plus cosine squared of theta equals 1. Okay. So in my next step, the integral becomes something quite simple. Now 1 plus another 1 right here. I'm looking at an integral from 0 to 2 pi. Okay, from 0 to 2 pi, and then it's a square root of 2 plus 2 sine theta. All right, and I'm multiplying that with d theta. So this is our complete integral and very ready for action right there. Okay, but then one more argument. So back on the picture. We notice that the curve for 1 plus sine theta itself is quite symmetric. It's quite symmetric. But then it's only symmetric. It's only symmetric in a way that it start out with the, if we start out with the angle negative pi over 2. So if I'm starting out with my angle of rotation, that's start with a negative pi over 2 down here. Okay, and I'm rotating that to pi over 2, then we will get half of the curve, and then we're gonna, from there, if we go further to a positive 3 pi over 2, then that's again complete a 2 pi rotation. But instead of using the interval from 0 to 2 pi, now allow me to modify my integral as from negative pi over 2 to pi over 2, but I'm gonna double. So instead of using this overall integral, okay, instead of using this overall interval right here, I am going to use a different version. It is going to be, okay, that integral from minus pi over 2 to pi over 2, okay, and then the same integral here. This is just a simplified form of that, 2 plus 2 times sine theta in the square root d theta. But this is only half of the loop. Okay, this is only the length of half of the loop. So now to get the total loop, we're going to double. Okay, we're going to double the physical length, and that's how we're going to arrive at the final answer. All right, and so now in that way, I'm going to move over to this board right here. So our integral at the current step is 2, and the integral from minus pi over 2, and so hopefully, you can always go back and review that part where I made my arguments about how I changed from 0 to 2 pi into a separate integral from minus pi over 2 to pi over 2, but then double that integral. But now with this current integral, okay, 2 plus 2 sine of theta d theta, okay, and allow me now to do the following trick. Very similar to that trick I did back in example 1 earlier. So now it's from minus pi over 2 to pi over 2. I'm looking at the following expression. So, and allow me to do one more step. I am going to factor out that 2 right here. Okay, factor that out, so it's going to be 2 times 1 plus sine theta. Okay, I'm going to factor that out, and then I'm going to take that 2 outside of the square root. So in my next step, it's better to write it as 2 square root of 2 times the integral from minus pi over 2 to pi over 2. Okay, and now we're having something much simpler, 1 plus sine of theta. Okay, it's just my style that I like to leave things in the square root as simplified as possible. Okay, as simplified as possible. So really, in the next step, 2 square root 2 is a coefficient. Minus pi over 2 to pi over 2 is the integral interval. But now with that square root expression, now I'm going to produce a big one here. The 1 plus sine theta is still here. But then I'm going to apply that trick that you have seen back in example 1. with this two terms here, 1 plus sine theta, I'm going to multiply the conjugate to that. The conjugate of these two terms is going to be 1 minus sine theta. Okay, but then as we multiply algebraically any expression to a given expression, we have to divide that, multiply the expression away. So 1 minus sine theta is also to be divided away. Okay, and then I'm going to multiply it outside of the square root. I'm going to multiply with the d theta. All right, and so now by doing this, it gives us some advantage for the next step right here. So in the next step, it gives me, now it's that 2 square root of 2 is still here. The integral from minus pi over 2 to positive pi over 2 is here. Okay, but then the numerator reduces down to 1 minus sine square of theta. And the denominator is simply just 1 minus sine theta. Okay, and then there's d theta. And that's how I'm reducing it. Okay, and 1 minus sine theta will be cosine square. I mean 1 minus sine square theta here will be cosine square, but inside square root for now. So in my next step, 2 times square root of 2, the integral from minus pi over 2 to pi over 2, but then it's a square root of cosine square theta over 1 minus sine theta. Okay, it's a square root d theta. And so now again, I am going to make that argument that the square root, I mean the cosine square of theta over here can be taken out of the square root, but in the next step it must become the following. So 2 times square root of 2 with the integral from minus pi over 2 to pi over 2, but in the numerator now I have absolute value of cosine theta, okay, divided by square root of 1 minus sine theta, d theta. So this is absolute value of cosine theta. It's the way how anytime that we're taking square root of a squared expression, okay, anytime you're taking square root of a squared expression, we will always end up with the expression itself without square, but in absolute value. Okay, but then now we're going to start making some arguments. Now, if we're looking at the picture right here, or we're looking at the unit circle itself, for any angle theta, anywhere from minus pi over 2 to pi over 2, then cosine of theta will be a positive or at least 0. So my point is that we know that cosine of theta is greater than or equal to 0 for theta is anywhere in that interval from minus pi over 2 to pi over 2. This is known fact from trigonometry. Okay, but now why do I use this factor here for this particular problem? Because in that way now we know that with our interval here from minus pi over 2 to pi over 2, then we can rewrite this simply now as cosine of theta without the absolute value sign, because the cosine of theta itself is already greater than or equal to 0. So there's no need to write that with the absolute value any further. So now I'm going to erase this and make space for my next step right here. All right, so now I'm going to have to erase the details of the work up here on the board. And so after that argument, now I'm looking at the 2 square root 2, the integral from minus pi over 2 to positive pi over 2. But then now I can write that cosine of theta in absolute value, but now without the absolute value. And then square root of 1 minus sine theta, okay, d theta. All right, and so now at this point, once we have arrived at this particular one right here, then again I'm going to use a substitution. I'm going to substitute the 1 minus sine theta with a variable u, okay, or I'm going to substitute all that here for a variable u. And so that means a du d theta equals a negative cosine theta, or du over negative sine theta, negative cosine theta equals d theta. Okay, and then when theta equals negative pi over 2, then we have u1 equals 1 minus, and then the sine of negative pi over 2, okay, which gives me, so this is a 1, but sine of negative pi over 2 is a negative 1, so it's 1 minus a negative 1, that gives me a positive 2 with that. All right, and then we have a u2 equals 1 minus sine of positive pi over 2, okay, which is a 1 minus 1, which is a 0. Okay, so now we can put all the substitutions in places here. So now it's an integral from 2 times square root of 2 multiplied with the integral from, now it's u1 is a 2 and u2 is a 0. Okay, just write it that way. And then we have cosine theta, which did not get a substitution for, but the square root expression now is substituted by square root of u. Okay, and now the d theta had a substitution. So d theta had a substitution du over negative cosine. So du over negative cosine of theta. So now the cosine of theta will cancel and leaves a negative sign in front. So in my next step, it's a minus 2 square root of 2. The integral from 2 to 0. 1 over square root of u du. But then notice, we have a very awkward, or it looks backward with the interval that goes from 2 to 0. From big to small. But then good news, we have a negative sign in front. So that means according to the property of integrals that we have learned, up to this point, anyone must have learned that. And so now we can change this to, now allow me to do this short trick right here. So I can now freely change this to a 0 to 2, but then skip out that negative sign. So we flip the sign anytime we flip the integral, anytime we reverse the integral order. Okay, and so now, once we have to this point right here, then we can think of this integral as a 2 square root 2 from 0 to 2 as the integral, but u to the negative 1/2 power, and now things will fall out just as usual. So here I'm looking at 2 square root 2. Now I'm ready for applying the fundamental theorem of calculus, where the first step now is to get the antiderivative for u to the negative 1/2. So what I need there now is 2 times the antiderivative of u to the negative 1/2 is 2 times u to the positive 1/2. Okay, and then this needs to be evaluated from 0 to 2. All right, and then how about a little more simplification? It's a 2 times 2, so it's a 4 square root 2 times u to the positive 1/2. Or how about let's write it as a square root of u. A square root of u, and then we're evaluating it from 0 to 2. All right, so now here's in my work right here. So now substituting in, I'm looking at 4 square root 2 times square root of 2. This is how I substitute 2 into the u variable, and now I'm going to subtract out 4 square root 2 times a 0 out, okay? Because due to that 0 in the bottom limit right here. And so now that whole term is gone. My final answer, and by the way, 2 square root 2 times square root 2 is another 2 right there. So 2 times 4, our final answer is 8. All right, so ladies and gentlemen, we have now found the length of the total loop that looped around. So in this picture, now let me return to the 0 rotation, okay? And now as we make one complete rotation, all right, as we make one complete rotation, look at how that loop is keep changing and keep getting more and keep getting more. So here we are at exactly halfway, and the other symmetric half of that is here. Okay, so that the whole loop now when it's finished looping, right? That whole loop here is at length 8. Okay, and this is the total length of the curve of r equals 1 plus sine theta. All right.